two selections, which are like composites, which I will be talking about later. And what was the reason to choose those parts, chose those materials? Because we see these materials, since they are lightweight, and we can reach like metal-like properties while keeping the part light. We see this as the future of aerospace industry, especially even for the structural components where they're going to be under load. So, for example, the former one, Onyx, is a nylon-based composite material that has chopped carbon fibers inside. And the second one, Peak, it's the version we are using has also chopped carbon fibers inside, which increases its stiffness and ductility. And then it's a high temperature thermoplastic. Then, continuing with our, you can see here on the table the shell values and the infill values we have used for those parts. And then, as I have mentioned before, because of the nature of additive manufacturing, there is some problems, there is some defects happening in the build direction, right? That's why we needed to decrease the properties in the build direction. And that's what we did, both for like shell values, infill values, and then on the table here, the end side, you can see that we have averaged some values using something called rule of mixture that we are going to be talking about in the following slides. So, when it comes to the approaches we have used, first one is called high fidelity model. Why is it called high fidelity model? What makes it high fidelity? So, we are basically assigning two different material properties to shell and the infill. And it is hard to, not hard, but it takes some time to model the part. But it gives very accurate results. But there is also a drawback here. The drawback is that since it's computationally expensive to assign two different properties to shell and the infill, it's like computationally expensive. So we needed to come up with something that can solve this problem. And that's what we did. We have came up with something called low fidelity model using rule of mixture. And what we are doing basically is we are using the volume fractions of shell and the infill to average the mechanical properties of them and came up with one uniform mechanical property that can be used for all elements. So not shell and the infill separately, but all in one uniform element and all in one uniform mechanical property. And for sure, it is changing by the volume fraction to the parts. You can see the fractions we have used for the specimen and the flange itself. And yes, after all is done, we have compared our results to the real life data we had. So if you see here the specimen we have tested, this is the specimen for the standard specimen that is used for the material that we are using. It is the polymer. And then after doing the test on these parts, we got the data. And then as you can see in the first table, we had very low deviation in the test results of the Onyx part. And then we have compared the results to the high fidelity model that we did. And as you can see, we are extremely accurate using the high fidelity model. Then, when it comes to the low fidelity model, we are still in the acceptable range, but keeping the model simple, which is very important. Then, to continue with the peak, you can see that there is a little bit of deviation in the peak part, which is causing, because as I have mentioned before, peak is a high temperature polymer, which has a melting temperature around 1,000 Fahrenheit degrees, which is a lot. So that is causing some defects while printing. That explains the like variation between the elastic modulus. But then still, when you compare the results, the mean result, with the low fidelity model, you can still see we are in the acceptable range while keeping the model simple.
So let's talk about the main character, the motor tension system. As I said, we are flying with a very, very high thrust motor. And for that reason, we have to be very, very precise with our model in order to validate our design. We've designed this part using topology optimization. So we actually optimize the part. Topology optimization is an algorithm that, following iteration, is going to basically remove the volume where it's not needed and keeping the volume where it's needed. And doing so is take into consideration the load case of the part itself. As you can see, we also printed the parts with two materials, of course, onyx and PEEK, and the goal is to compare the two and choose which one is better. So we also performed a compression test in order to validate our FEM. And as you can see, talking about a bit more about the setup here, we have like the white and orange body tube is a shorter body tube of the real body tube we are flying with. It's a carbon fiber laminated body tube, and inside of it we have the component that is screwed with 8 M5 screws that are connected to the part with threaded insert. We use the threaded insert, are very very useful for our purpose and very strong. Also, another important thing is the forward closure. We basically using the forward closure of our motor also for this test, and then the machine is applying the force with the upper brackets into the forward closure, and then it's also needed for evenly distribute the loads onto the loaded surfaces. Then we can also see that the machine is, of course, measuring the force that is applying, but also the displacement. He's measuring the global displacement that we have on that part. So yes, the machine basically is going down and is measuring the millimeters. Going on, we can see the video of the test. I'm just explaining you what you're seeing there, of course, the test. And here on the right, you have on the x-axis the global displacement, compressive displacement in millimeters. And on the y-axis, we have the force in newtons. So let's go. Yeah, if you watch the screws, where the screws are, the inserts are, you can see a little bit of displacement, not that much, but as you can see, 3 millimeters of displacement with onyx. Then let's go with the PEEK. Remember that PEEK is very stiff, so we expect a bit less. Yeah. Yeah, it's hard to notice, but it's 2.4 millimeters, so we are safe on that side. Then, going on, as we said, we have finite element analysis. We carried out an analysis using Altair Hypermesh software, and we also implemented our low fidelity model that my colleague said. And using that, we also meshed the part using a very fine mesh, and it's a trade-off between keeping the geometry as close as we can, but at the same time being very precise on our analysis, and also keep the computational cost low. Talking about the result we have, you can see that on the left PEEK and on the right onyx, the displacement map is very similar between the two materials. So the blue are for the where the displacement is lower, and red where it's higher, of course, in the middle of it, where the motor is pushing with very high thrust, the displacement is a bit higher. And then we have, from this analysis, we had 0.6 millimeters of displacement with PEEK and 1.6 millimeters with onyx. But as you can see, if you remember the previous compression test, now we are seeing a lower displacement. And that's because we are only considering the elastic deformation of the parts with our FEM.
So, as Andrea mentioned, we are only measuring the elastic displacement happening in the flange. But there is also, we are aware of the fact that there are displacement happening outside of the flange that we cannot measure because we don't have the whole setup in the FEM analysis. So in order to solve this problem, we have came up with a linear system of equations, and once we have at these values, we have seen that we are very close to the real life results. So as you can see here, these relations show the total displacement is equal to the displacement happening outside of the flange, plus the elastic displacement happening in the flange, and then same for the peak part. And then there is a relationship between the mechanical properties and the elastic displacements for sure. And using this system of equations, the 3 equations you see on the top left corner, we have calculated this function. It's a function of force, saying that for how much force you have, the total displacement you have in the non-flange area. So to continue with the final results.
Yeah, so these 2 graphs are representing our final results. On the left we have onyx, and on the right we have peak. The continuous line is for the compression test we've done, and the dotted lines are for the low fidelity model coming from our FEM analysis. As you can see, the first thing we can notice is that in the continuous line, so the compression test, at the beginning we have a non-linear part. That's due to the non-flange displacement. So the flange is actually not deforming that much in this phase, and it's not linear. But then, after, kind of in the middle, we have the slope is constant. So we have an elastic linear field. So which means that the part is in its elastic field is behaving, is deforming, elastically deforming, and we are. That's of course good because we want to stay in the elastic field. We don't want to go in the plastic region, and the line keeps straight. So that's good. The slope it's constant. Same for peak. You can see at the end. Then talking about our model, of course it's linear because our hypotheses were linear, static linear. But then you can also see that for high thrust, for high force, we have the slope is lower compared to the real result, which means that the slope represents the stiffness. So this means that our model is actually underestimating the stiffness for higher forces. And that's very good because we want that, because our model is, from an engineering perspective, is underestimating the stiffness of the material, and we kind of have a safety factor. We are safe on that side. Yeah, then the conclusion. Of course, after this validation, we know that PEEK is the best of the 2 materials because it's much stiffer, much resistant, and also he has crazy thermal properties because PEEK prints at 500 degrees, so we are also safe at high temperatures. At the same time, we know that we can do better. In the future, we might introduce some new ways to estimate the properties of our orthotropic material to improve our low fidelity model. And then we can also say that the linear hypotheses were a bit too strong, and we can improve that introducing some non-linear system of equation, for example, for the non-flange displacement. Yeah, that's it. And basically, we validated our design. That's the important thing. And we know that with 3D printing, it's very difficult to understand the behavior of that part. But if we find a realistic model that is comprehensive in terms of it's actually, understanding the behavior of our material, how it's deforming, we're safe on that side. We know that, yes, we are safe. Thank you for listening.
These are the actually flanges that has been tested on the machine, and the one that says peak is peak, and the one that's onyx is onyx. If you have seen maybe during the onyx one. And we can have the questions. No.
I have questions.
Yes.
What about repeated stressing? Is peak
for the test, we haven't done the test on that side and also in the analysis side, but for the future, especially for the, let's say, reusable of the flange, it should have been done and it should have been taken into consideration, if I understand your question well.
If I can, if I just want to add something, we also repeated the test 2 times on each flange. So in each system, the test 2 times, and the results were pretty similar. So
Feel like it returned
exactly, yeah. That's also, you can see if you check the exactly, because which means that we are in the elastic field. That's the important thing. We know that we are in the elastic field. There is no plastic deformation, or not that much, so we are safe on that side.
And what were you trying to achieve? I mean, this could have been the machine from Olympus. Why did you choose additive manufacturing?
Because we like use a lot the processes like topology optimization and generative design, because we believe that it allows us to go lightweight with our material, and when you go like complex geometries, additive manufacturing is the way to do it, because it's so hard to machine complex geometries using traditional machining. So that was the reason. Yes. We are using a software called NTOP. They're pretty new, but they have a lot of cool features for topology optimization. They have also some features for lattice structures and also doing the infill of the parts. So it's a very good software. So basically, it was the reason of the not problems, but license stuff. So it was easy access to get into the license. So that was the main reason we have used that software. No. Uh-huh. It's called Apium P220. No, it has only one nozzle, but as I have mentioned before, also the peak version we are using is called Peak CF30. So it also has like chopped fibers by the weight of by the weight ratio of 30% in the material. So that helps a lot, but no, that printer doesn't have the option to continuously reinforce the part. We actually did that the test of that one as well, but since, as you may know, the simulation of the fibers inside the part is quite hard, so it was very hard to simulate it on the FEM software. But in the future, we also want to like get into consideration of using that one, because that's also very important and that's a very useful feature in our thinking.
So yeah, that's a very good question. We didn't introduce the Onyx plus carbon fiber reinforcement because it's very difficult to validate a model with that. Actually, maybe it's something we can do in the future. But as of now, the the Onyx plus carbon fiber was worse than Peak. So we had actually a higher displacement with that. So Peak still the best.
So okay, so if I understand your question well, uh, we have been decreased the properties only in the build direction. So we did the same for the shell and the infill for build direction, but we have kept the property same on the plane, so X and Y. And it's the same for the infill and the shell, but the only thing we did for the infill properties, we have decreased it, we have multiplied it by the infill percentage, because it has like 37% material inside. It's not fully like solid. That's the reason we have decreased the properties. And also on top of that, we have decreased the properties only on the Z-axis for both the infill and the shell, if I understand and answered you well. it's the chopped fibers is around 0.1 millimeters long, and when you randomly distribute them inside the piece, it adds a lot of homogeneity in the plane and also like in the build direction. But the problem with the build direction is the defects happening when you go layer by layer. It's not the fibers.
I guess I was thinking like the lattice infill, like
Mm.
more the macro geometry of that.
Mm.
Like
No, for sure the geometry of the infill helps with the part, but when you go with like the infill such as gyroid, they are assumed pretty isotropic in the literature. Yeah. Okay. Any questions? No? Then we can finish, I think, yes.
Can I get a picture of you two guys with your
For sure, for sure, for sure. Yes, I want the Onyx one.
All right, good deal. Thank you. The judge, so I had to advocate for your product.
Thank you. Thanks a lot for the time.
good. I love that.
controls,
Yeah.
and now diesel electric hybrid drivetrains.
Hmm.
A little bit of everything. Do you have another judgment here, Stacy? No, I'm solo. Okay, great. You got
Cool. Go ahead and get started. Alrighty. Alright, good to go. Cool. All right. Hello, everyone. We are Team 312, Texas Tech University. We have something interesting to present to you guys today on our solid rocket motor. Something interesting that we found on our solid rocket motor development journey. My name is Kyle Markle. I recently graduated with my degree in chemical engineering this May, and I was our Space Raiders director this year, so I was the lead for the rocketry team.
Hello, my name is Olivia Lira. I'm a mechanical engineering student, and I am the incoming Space Raiders director for 2025-2026. This year, we are competing in 10K SRAD, which means that we've had the pleasure of, over the past year, designing, manufacturing, and testing our own solid rocket motors. And in that, we found some really interesting things during our last static fire, and today we want to share those with you.
Yeah, so a little bit of details on the propellant we're using. Obviously, we're, like Olivia mentioned, we're competing in the 10K SRAD category, which means that that requires a significant testing campaign for our blue propellant. And I've outlined the exact formula over here, but just some highlights. It's an ammonium perchlorate composite propellant, or APCP. And it also includes aluminum powder as a fuel and copper oxide as a burn rate catalyst, and then as well as obviously ammonium perchlorate as the oxidizer, HTPB as a binder, and MDI as a curative. And then we have a few other additives and things for ease of pouring and other things like that. I'll highlight the aluminum powder and the copper oxide, as those are kind of the majority of materials that we're going to be looking at in this presentation today.
So like I mentioned earlier, during one of our last static fires, we found something really interesting happen to the nozzle. As you can see on the photo to the right here, we saw a pretty significant amount of slag buildup. And I would like to note that the slag is actually flush with the nozzle, but for taking this picture, we moved it up a little bit so you can see it better. So we decided, we saw this, we were like, this could be pretty cool. Let's try to figure out what it is. And so slag is primarily contains aluminum. Aluminum and aluminum oxide. Aluminum oxide is the combustion byproduct of aluminum. So the presence of aluminum oxide would indicate that we had complete combustion, and the presence of unburned aluminum would indicate that we did not have complete combustion all the way.
Yeah, so if you remember from that propellant formula slide, most of the propellant combustion products are generally expelled in a gaseous state. So all of your, carbon materials, things like that, those are mostly gaseous. However, usually that doesn't happen with aluminum based propellants, especially at the smaller scale that we make motors at. And aluminum, sometimes, and a certain amount of it is usually expelled as in a molten form. This is a pretty well documented phenomenon. It's commonly seen in video and photography of motor burns. You can see this was footage from one of our previous motor burns, and you can see a lot of the aluminum coming out there. And so as aluminum particles flow through the nozzle and you have the gas exiting the nozzle, simply due to the geometry of the nozzle, you're going to see a lot of that aluminum build up on the nozzle. A lot of it is going to agglomerate due to the geometry. You can think of it as a funnel with the gas flowing through it and the aluminum kind of getting caught and hardening on the nozzle as it exits.
A little bit more about our motivation and goals. Like I mentioned earlier, we really just wanted to learn a little bit more about what's going on in the aluminum and ACPC motors. So to do that, we're going to review the composition and morphology of the slag through multiple analytical techniques that we will talk about later on in the slides. The first method that we employed was X-ray diffraction. Essentially what's going on is we have a powderized sample and we're shooting X-rays at it, and those X-rays diffract at a certain angle, and that diffraction angle creates this graph here to the right. I would like to point out that for every sample that you take, these small peaks here, sorry, can I see that? These small peaks here are unique to every kind of sample that you take. So that's one way that one of the ways that you can find what your composition is by comparing the graph that you got from your sample to well-known documented graphs. And I will go a little bit more into detail about this later. And X-ray diffraction is widely used in the scientific community. You can find phase composition, more about the crystalline structure, and some more about the physical properties. We employed this method on our samples because it is a non-destructive method, and it could give us a little bit more understanding of what we were actually working with. I will say one thing about this method is that because it can only see crystalline structures, you're not going to be able to see more complex components come up on the XRD. During the sample prep for our XRD, like that photo is there, we had to break it up to powderize it. That's what the machine takes. And while we were powderizing that sample, I broke it off and I found this really interesting cross-section here that reveals that there is a high presence of alumina here. Alumina has a characteristic and a tendency to be white. So when we opened up this cross-section and we saw all of this white, we were like, well, this is aluminum. I would also like to note two things about our sample preparation. For the converging section of the nozzle, I used a mortar and pestle to powderize the sample, and for the throat section, I scraped that with a razor blade because it was very, very difficult to powderize it just using a mortar and pestle.
So the second laboratory analysis technique that we used was SEM and EDS. SEM is scanning electron microscopy. That basically exposes the sample to a beam of electrons and measures the response of the sample to that measures the response of that sample to the electron beam and creating an image at a very, very high magnification that's not possible with optical means. And then alongside that, we can also use EDS or EDX. Those acronyms are used kind of interchangeably. And that's energy dispersive X-ray spectroscopy. And that measures the energy and intensity of the X-rays emitted by a sample when it is exposed to the electron beam of an SEM. And that measures the elemental composition of the surface of the sample. Usually it's about 0.5 to 1 micron depending on the exact composition of the sample. And you can see here, basically it's a long electron beam that, and you have a lot of sensors to create different types of images. So for the sample preparation for the SEM, we took 2 samples again, kind of similar to the XRD. We wanted to take a look at the converging section as well as the throat. And so we wanted to take a look at this cross section. Like Olivia mentioned, we found this very interesting cross section here, and we wanted to learn a little bit more about it. We also wanted to take a look at the inner surface of the converging section of the nozzle because that surface was kind of interesting to us, and we wanted to see what was actually there. So these are some of the SEM images that we obtained. On the left here we got the nozzle throat. On the right here we have the nozzle converging section. These are at these are at a 500 micron scale, so the width of a human hair is about 2 of these lines here. So we're looking at really, really small features. What we're looking at here basically is this bottom layer here is the closest to the graphite nozzle. And then this middle layer here, this is the layer that appears white under visual inspection, and that's where we are seeing kind of a smoother feel. You can see that there's a lot more carbon bumpy features here, as well as a lot of different copper deposits here. And we'll talk more a little bit more about the copper in a minute. But then we have this bottom layer, middle layer, and then we have the top layer. This is the one that's furthest from the nozzle surface, and that contains the materials that were last to deposit on the surface. And you can see the similarities between these two with a very clearly defined middle point. This was an SEM image of the surface of the converging section, and it was very interesting because we saw a lot of different morphologies. We saw a lot of various sizes of copper deposits. These white spots are the copper deposits, and we saw them all the way from a size of more than 40 micron to very small, even less than about 3 micron, and you can notice this the copper deposits tend to be very spherical, very uniform. The aluminum deposits don't seem to be that way. We have smooth spherical deposits of aluminum that we don't necessarily see in the cross sections. We also have extremely very small spherical deposits that almost look like dust, even at this scale. This is an EDS image. This is colored. I don't know if you guys can see that too well, but this is colored, and you can see the pink colors, and that's color coding for copper. And then on this image, you can see these white spots. This image type responds best. Lighter colors is going to mean a heavier element, which is why we know that these white spots are mostly copper. So you can see a lot of different circular, very spherical copper deposits. This is some more EDS data. This is specifically a spectra that we're able to obtain from the EDS data. We're seeing a higher aluminum concentration, aluminum and oxygen content at the throat of the nozzle compared to the converging section of the nozzle. And we're seeing a higher carbon composition on the converging section than the nozzle. And this is roughly consistent with our visual observations that the converging section seems to be a lot more carbonaceous with a lot more carbon-based deposits. I'll also note that we saw a good amount of copper in here as well, up to about 3.3% weight, and obviously this is a surface assessment of the composition of the material, so it's not complete, but it is a fairly good representation of the surface.
To dive into a little bit more detail about our XRD, these graphs on the right is what we received after the analysis done by the computer. So this is the converging section, this is the throat section. And like I was saying earlier, each time you run a sample, you get a graph with unique peaks. And the way that you figure out what the composition is by matching it to a reference database. So here, diamond, this is going to be carbon. If you look here on the converging section and you look around 45, you can see there's a peak around 45 that matches up there. If we go down to the corundum, which is just another word for aluminum oxide, you can see, let's see, if you go here to 25 and then you go to this graph here, there's 25 there. If you go to around 35, there is another 35 peak there, so on and so forth. You do not do these by hand. A computer does them for you because looking at all of these peaks would be kind of crazy. So yeah, some of the XRD data that we did get was that we actually found a 12% decrease in alumina from the converging to the throat. And we believe that this could be because the throat sample, like I mentioned earlier, it was not a well-rounded sample. Because I only scraped the surface of the material, I did not actually powderize the entire section of that material. And for this reason, we believe that the SEM and the EDS is a better reflection of what the actual composition is. For future work, we think that we could get some better samples, higher resolution SEM images, to just get a closer look at the actual morphologies. We could also do more detailed or comprehensive spectroscopy, Raman spectroscopy, or maybe just more XRD runs or SEM and EDS runs. And we could just do a little bit more extensive literature review, see what the scientific world has seen, if they have seen something like this as well. I would like to give a very special thank you to Space Raiders Propulsion team for the research, design, and integration of our solid rocket motors. We could not do without you. Dr. Zhao for SEM imaging, Dr. Malami just for some guidance, and Mr. Booley and Mr. Mikas for help with our XRD analysis. I want to thank you on the behalf of RAS. Thanks for coming to listen. We're glad we got to share this with you, and if you have any questions, we're happy to take them. For the XRD, we did 2 samples. Like we mentioned earlier, we did one from, sorry. Go back to the slide. Here we go.
I'm saying I'm kind of mesmerized by the imagery, so.
Yes, okay, see,
Okay.
so those are the 2 sections that we took. Yes, I will say seeing SEM imaging for the first time is a little bit intimidating because you're kind of like, what am I actually looking at? But yeah, we took 1 section from the throat, 1 from the converging. And I will say that the reason we decided to do this is you can obviously see there's a pretty big color difference in between these 2. So we thought that perhaps there would be a higher aluminum content in the throat just because of the color difference. That was one of the reasons. Do you have another reason to add? Yeah.
And then for the SEM, you were looking edge on at that cross section that you had. Is that what you were focused on looking?
Mm-hmm.
And so that, I would assume that gives you a better insight into what the profile is. Were you able to image that in a number of the locations and compare the compositional information across the layer?
Yeah, it takes time to do a lot of these runs, so we weren't able to look kind of layer by layer. What we kind of did was this image here is kind of the most representative of the cross section, where we have all of those 3 layers together. We did kind of zoom in to a couple specific spots, but we didn't necessarily have the time on the SEM to be able to zoom into exactly everyone.
So if you didn't have those time constraints or other constraints, what further measurements or analysis would you like to do?
Yeah, I mean on the SEM, I think looking closer at certain surface features on the converging section would be really interesting. Those features are actually really interesting. I'd love to learn more, especially like Olivia mentioned. We'd love to do some more higher resolution SEM, and that would hopefully give us a little bit more information about the really small particles. And then yeah, looking at each of these cross section areas would be great. I'd love to learn more about each cross section for sure. And Olivia can speak more to the XRD stuff too.
So is there a way for you to, through your data analysis, is there sufficient information there for you to determine how much of the aluminum, since it's your fuel, was fully oxidized or not?
Not really. We did have Dr. Zhao pointed out that this EDS data is given in atomic percent. So, and it's obviously aluminum oxide is Al2O3. So you should be able to kind of ratio this out and figure it out. The only thing is it's not super representative of the entire thing. And so, like, obviously we're taking very small measurement. This is, really tiny. You can't even see it, square of information. And so, like, I mean, yeah, you could kind of ratio this out and see that, you probably are going to need some more oxygen to fully oxidize that. Right, but it's difficult, and obviously, yeah, you might have some, carbon, copper oxides, things like that, that are trapped in there. Yeah.
To reiterate another point too, the SEM and the EDS is only looking at the surface, just so it's not a. Yes, except for we have the cross section, but that's a reason that we chose XRD is because it is a little bit more well-rounded understanding of what is going on there.
So, what do you think about the impacts on your motor performance from this?
We think what we found really interesting is just the presence of just the copper. That was something completely unexpected. When we went in there, she was like, "We have an awful lot of copper in here," and we were like, "Really?" Which is another interesting thing because we didn't see it in the XRD at all, and that's something we would like to look into more. But as far as motor performance, what do you think?
Obviously, with the slag in there, you are kind of constricting your nozzle a little bit, so there's that. And then, yeah, the biggest indicator of performance, I think, would be looking at this slag and figuring out how much of the aluminum is oxidized, because obviously you add that as an efficiency boost, and if you're not burning it all completely, then that could inform further decisions. But yeah, I think that's as far as we could go with that.
So any other wish list items that you
Lab equipment is really expensive. But yeah, I would really like to look at some Raman spectroscopy data. You can see a lot of it's a more comprehensive spectroscopy method. It gives a little bit more information than XRD, and that's something that it's something within a material like this. It's hard to extrapolate across like the entire sample. But I think Raman spectroscopy across a few different samples could give us a good idea of kind of the gradient of the materials that we're looking at. So
That's all I have. Does anyone else?
Any other questions?
Do you have any explanation, do you think, for why that aluminum oxide layer was sandwiched between two more carbon-heavy layers?
Yeah, we think it has to do with just the general like process of combustion that's going on in the case. So we think that during the bulk of the burn, that's probably where a lot of the alumina came from.
Right, and then that end might be when the
Yeah.
liner is burning.
it's like
Yeah.
your
Yeah.
pressure ramp and
Mhm.
yeah.
And then I guess on the bottom of that slag, it was a graphite nozzle, right?
Mhm.
So I wonder if that nozzle was also
Yeah. That contributes to. I think that contributes to some of the carbon in here as well. It is. It is. It's a little sandwich. Anything else? Yes.
Based on what you guys found, do you think alleviating the slag could be accomplished by changing your propellant formula or just changing the nozzle itself?
Yes, I think that could. I think we could alleviate some of the slag by that. But as I was saying, aluminum oxide is just a byproduct of combustion. So no matter what, if we use aluminum, we're gonna have some kind of byproduct come out.
And I'll just say, kind of, we talked about kind of the mechanical methodology of how aluminum deposits. Like, it's kind of just a byproduct of having a nozzle. You can't really prevent the slag entirely, but I mean, you could try to minimize it by making your aluminum particle sizes smaller, using less aluminum, so it's more well combusted. Things like that is what I would say. Cool. Any other questions? Cool.
Thanks, guys.
All right. Thank you.
teste. It's not on. Ah, ok. Ok, that's fine. Meu cara já fica virando.
Respira. Conta 4. Segura 4. Solta 4.
Okay. Hello everyone, welcome to the Team 313 Podium session presentation. Today I'm going to present Machwave. Present.
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 Present. Yes.
Eu não vou conseguir falar present.
Só fala presente. E tira o E.
Today I'm going to
Present.
Today I'm going to present.
Present.
Present. Okay. Today.
E Python é Python.
Ah, vamos ver.
That's alright. If you need me to explain something, you can just
Ok.
pass me the. Just faz assim que eu falo.
Tirar o som do meu celular, né? Importante. Minha calça tá direita. É que eu tava sentada no chão. Abre o roteiro aí, rapidinho. É financilo, né?
O quê?
Abre o roteiro, rápido. Vai até o final. Can? Okay. So, hello everyone. Welcome to the Team 313 Podium Session presentation. Today I'm going to present Machwave, a stochastic solid rocket motor simulation Python library. So, just for a bit of context, we are Supernova, a Brazilian rocket and satellite team from the state of Minas Gerais. The team started in 2015 and has currently 47 members. This year, we brought to the 2025 IREC our rocket called Podium. It is a 10K SRAD solid rocket motor. So, as a mainly solid rocket motor team, our performance is highly sensitive to interdependent and nonlinear parameters. So small deviations in parameters like throw diameter, propellant mass, grain geometry, or burn rate can produce big variations in the pressure or chamber pressure, in the chamber pressure or interest, even leading to a catastrophic failure. So that being said, Machwave just integrates the full system, the full design of solid rocket motor, including this process in Python. So we have the thermochemical properties, we have the internal ballistics, structural sizing of casings and retainers, and the integrated point mass trajectory estimation. So all of this we can wrap in the Monte Carlo simulations, and it can export time history charts and statistical summaries. So for the internal ballistics, we use the RK for equation solver, differential equation solver, to the transient chamber pressure. And for the computing of the thrust coefficient, we use the isentropic relations. So our program can support officially many geometries of grain, including 2D and 3D geometries. Here in these two images below, we have two examples of geometries that are supported. So we have the multiport grain geometry and the star grain geometry. So as Monte Carlo is an important part of our program, I'm just going to give a little brief of what it's about. So in Monte Carlo, we can grab like random values and generate a sample of probable outcomes. So each scenario is run separately, and when we have a large amount of results, we can determine the probability distribution. It is reliable. So for running the simulations, we have 3 big steps. So the first one will be the predictive model. So we use the internal ballistic solver in a deterministic model to start the program. After that, we have to generate the scenarios, defining all the variables that we're going to need, and setting the probability distributions and ranges and the quantity of scenarios that we're going to run as well. So as our final step, we simulate the scenarios, each one being simulated separately. So we use our deterministic engine. So for our case study, it was chosen the Olympus. Olympus is an O-class motor. It was developed in 2022 by Supernova and Minerva in Brazil. So at the time, it was the largest experimental solid rocket motor tested. So the motor was tested on July of the same year, 2022. And here you can see a picture of the static test of the motor. So in this motor, we use 7 grains of propellant made with K and SB. That is a mixture of potassium nitrate and sorbitol. So all of these grains, they are cast manually. So with that, we can produce we introduce in the process some significant variability in the process of manufacturing these grains, and also in the process of machining our nozzle. That is a big part of our project. So we use this variability to put in our program to generate a more accurate result. So here in this table, we have all of the parameters that were used in this case study. So for the core diameter and the outer diameter as well, we use a tolerance of 2 millimeters. And for the segment length, we use a tolerance of 5 millimeters. And for the nozzle throat diameter, a 0.5 millimeter tolerance. So all of those tolerances were determined using the deviation on the measured 21 grains that were manufactured for this motor. So all of them was measured, and we used those deviations to fit our program. So the probability that I said before that we needed to set for the program, we chose a normal distribution, and the tolerance was defined as 3 times the standard deviation. And for final preparation of the software, we choose to run 10,000 scenarios. So here we have our first plot of results. In this plot, we have the lowest, the highest, and the median mean of the chamber pressure through time. So here we can see the deviations of the chamber pressure through time, okay? So in the second plot, we have the cumulative probability of the total impulse. And this one, it is a histogram and a KDA trace that interpolates the histogram occurrence to generate a trace that better fit the histogram. So here we have the occurrence of total impulse and the density. Okay. So finally, we have our statistical summary with all the values that were generated combined in those two tables. So in the first one, we have the total impulse data. So it includes the mean, the median, variance, the standard deviation, the mode, and the probability, as in the second plot that I show you. That one. And in the other side, we have the mean chamber pressure. So we have the lowest, the average, and the highest mean values for the Olympus motor. It is important to say that all of these 10,000 scenarios we run them with an execution time of almost 1,000 seconds. So in conclusion, Machwave is an extremely powerful software for us that work with solid rocket motors, because it can predict possible failures or possible problems with our motor burn or the pressure inside the motor. And it also ensures a better understanding of how the conditions of the environment and mass grain and the conditions of the propellant, the geometry, can also affect the conditions of the motor and its burn, right? So the Machwave has been already used by many universities and many teams, and it was also used by our team many times in different motors. The first case was the Olympus that I showed to you. At the time was the largest motor in Brazil. So it was a class O. And we used that after in our currently motor that is called Icaro, and class M motor. And for future work, I would like to say an important step for our program would be to add the liquid and the hybrid motors to the program, and also like extend the toolkit of the program. We are always trying to optimize it and bring in new tools to the program so more teams can use it. So here we have our reference. So our source for every calculation can be found in the code base inside the doc string of the function or model of the code. And some of the main sources for this work are here. So we have the program and some books that were used for inserting the equations that we needed to solve all of these cases. So thank you, and feel free to check out Machwave on GitHub and to give us any suggestions. We are open to it. And do you have anything? Eu queria ver o cronômetro atrás de você.
So one of the ways that we can upgrade Machwave to make separate the injunction with the hybrid and liquid is to separate the grain, because the solid rocket, you have the oxidizer and the fuel all in one, and the liquid and the hybrid, you have to separate the two. We have to put the coefficients with transient, the fluctuant, the mechanical fluids, and try to make the adjustments for the expansion of the liquid and solids in the equations that we can make right now. For now, I don't think there is a timetable for the upgrade for the liquid and the hybrid. But okay, so we can make the adjustments at any time, but we are trying to make a steady progress. Right now, I don't have a timetable, but it's okay.
So just to add it to what he said, we like to keep our works in parallel. So as we were working with a new motor, the Olympus, the Class O motor, we started developing this program and using it to prove the program was reliable. So the program was validated at the time with the hot fire static task of Olympus. We were able to extract those data and match with the data that we have as an output of the program. So it is a work on progress, but we don't have like a deadline for this because we are like working on a theoretical project of hybrids and liquids and feeding this program with all of those data too.
So, from my understanding, Machwave was developed, it was validated using Olympus.
Yes.
With an O motor.
Yes.
Using a static fire.
Yes.
Now, is Machwave being used for the N motor that's flying this week?
Yes.
Okay. And how are you gathering that data to validate it?
So our currently motor, the Icar that you just saw, he was launched a few times. We brought him last year to the spaceport. We made an independent launch with him as well, and a few hot fire tests and hydrostatic tests. So we gather all of this data of past launches and past tests to match the Machwave data.
Right, but in a static fire, you're able to get load data from load cells and so on. But in a launch, are you gathering data from the flight computers? Is that the only source?
One of the things that we can gather, I think, the last time we saw the impulse and we can figure the impulse and the g-force that was used to propel the Aspera 2, which was the last rocket. But we could, from the two static tests, we could gather the data and we can match it with some of the tests we can run a Machwave, and we used some of the other burn sims that are available to see if the process and the result after the process and the computing of the data is actually the same, or it's matching, or it's near. Did I answer your question? I don't think I did.
Kind of. If you go back to the one where you're pouring and setting up the grains.
Yes. This one?
Yeah. So you've got a process to manufacture your grains.
Yes.
Yes.
And then in the next slide, y'all gave the nominal values with the
Yes.
tolerances.
Yes.
How are you measuring to verify that your tolerances have been met, and why that stack up?
The thing is, the nominal value from, for example, the diameter of this core, the thing is, the 45, the nominal value is from the core, this nylon piece. From the grain, the inside value of the diameter, after we dismold it, the grain, we check 4 or 5 points to see if the diameter check put on a Excel sheet and see the tolerance if it varies. Some may be 45.2, 45.7, 45. They might go up or down.
0.2.
It's 2. Sorry, it can be 47, can be 43. It can change. So that's the tolerance. They stay around the same, but the thing is, after we dismold the grain, we fabricate it, we measure everything, the length of all the propellant, there is a space between this one doesn't have, but in Icaro there is a space between the propellant and the other one. So there is a bit of the the fiberglass that is up. So we measure everything. We made all the calculations for it. The tolerance becomes for all the 21 that we manufactured for Olympus. We made the tolerance. It's the deviation for the optimal or the theoretical
So the
one.
tolerance was achieved through analysis.
Analysis, yes.
That's what you're meeting.
Yes,
Not the other way around.
yes, yes. And we gained the tolerance after we made and check with the theoretical numbers. The core diameters are the same. Everything for the outer diameter, which is this one. It-
One of the other interesting things that you all pointed out just now is if you go to the previous slide, you said there are 7 segments.
yes.
And you mentioned when you stack 2 segments, there is a gap.
Yeah. In the Olympus, I don't.
The parameter, is that still considered within the simulations?
Yes, not for Olympus, but for Icaro, yes, because we considered that the length of all the length of the motor is the one with the length of the grain. It's without the strip of the fiberglass that we carry for the combustion chamber, but this for Olympus it doesn't have that. This is an analysis of Olympus, not for Icaro, so there's this change. But in Icaro there is this. It's considered that that it's factored for a. I don't know how to say that, but it's a it's a space that you have between the grains for to fill all the combustion chamber. And yeah, that's just for the Olympus. It's a full core, and the Icaro it's not a full core like that. It has this little gap, and it's considered. We have in Icaro it's the same. For Olympus it's 7 grains. Each segment it's a grain. In the Icaro it's 1 through 4 it's 46, and in the core diameter of 5 to 7 it's 32. So or the opposite. So yeah, because the Icaro it's smaller. It's M motor. It's
Segments 5 to 6, is it on top of the?
if you think about I think this one it's the in the bulkhead, and then goes down 7. It's the most closest to the nozzle. So and in Icaro it's the same thing. You have the 32 on the top, and then you go down for 46. And the bulkhead is 32, and the nozzle it's 46. I think that you can we using the histogram and the cumulative probability of total impulse. Here is the impulse of the 5%, and the 95% is the most accurate.
Cumulative probability.
Yeah, for the impulse. This is the probability of the 5% being below the 5%, and this is the probability of the value, the total impulse, being below the 95%. And I'm sorry, but it's in the beginning.
So you basically just see if the theoretical values of your project matches with the outputs from Machwave. So you're going to analyze the chamber pressure, the total impulse, the truss curves, and see if it matches with your project. So we have the probabilistic part where you can see show. Okay.
This one or this one?
So the probabilistic part of the cumulative distribution of the total impulse. So you basically see if your project is most probably inside the range that you want for the total impulse. And the same thing can be seen for the histogram and the other plots. So the program also has like another function that is a open source code, so you can check on GitHub and see all of the geometries that are there officially for you to use in your project. It is also important to say that we use a fast-Martin grain regression method, so you can also add your geometry into the program.
Current grains follow which profile?
Sorry?
The current grains that you built?
No, we use the Bates geometry for our grains.
Okay, so it's not.
No, it's just an example of some geometries that our program can support officially. And as I said, you can also add the geometry that you want, fitting the program. So here in this plot, we can also see the thrust and pressure through time. So we can also match this with our theoretical data. Passa pro GitHub.
That's higher than that.
Okay. Bye. Thank you.
Check it out.
Very sorry. You're not the smart. No.
Good? Okay, okay. Hi, I'm Natalie. I'm the Composites Research and Development Lead for the Case Rocket team at Case Western Reserve University. And I'll be talking today about our team's designing and manufacturing of some forged carbon fiber flaps. So this was the team's very first time putting a complete air brake system in a competition rocket. So we needed to figure out how to get the flaps. We considered outsourcing them, but the flap itself has very specific geometry, and it would have been very expensive to try and outsource it. So we decided we would prefer to make them in-house. We had a couple materials options. We considered using metal and trying to cast them, but the key part of the flaps that we wanted to have, we wanted them to be lightweight, low cost, and high strength. And trying to develop a metal system to try and make these flaps didn't really check those boxes. So we decided to go with forged carbon fiber. And we had never done this before on the team, so we had to develop a new manufacturing technique using a 3D printed mold. And the molds for this process undergo a lot of pressure, which means it requires a lot of material to withstand the compressive forces. So one important part was that we wanted since we had to make 4 flaps, we wanted the 3D printed mold to be reusable. Otherwise, we would have to reprint the same mold 4 times and use a significant amount of material, which would no longer be low cost. So the first step of that was designing the mold. We already had the air brake design in CAD from the air brakes team, so we were able to just design a mold around that and tailor it to our goals. So we decided to make a multi-part mold. It ended up being 5 parts total, and that was to make sure that in case of any mold release failure, we would be able to break away different parts of the mold or only need to damage one component of the mold rather than having to, say, destroy 2 entire parts and reprint the whole thing. So that's one of the first pieces. This is the cap piece, and that makes the reverse surface of what you see on the flap here. And you can see those little cones are to mark the corresponding holes here, and that was to prevent us from having to measure out the hole locations after the part was complete. It basically pre-center drilled them and pre-marked them for us, which was really convenient. And then another important feature are these chamfers around the outside. And this is, again, to be able to pull the mold apart in case anything gets stuck. We could just jam in a screwdriver and twist a little to open up the mold. So again, it had to withstand a lot of strength. So we printed it using PETG and 45% gyroid infill on a bamboo printer. And we used 3 wall loops for all of the parts of the mold. And then after it was printed, we sanded all relevant surfaces to 2000 grit. And that's basically any surface of the mold that would interact with the surface of the final part itself, as well as these walls along here, because that would interface with another component of the mold. And then these are 3 more of the parts. These 3 basically form the center portion of the mold. We have 2 wings, which are basically just mirrors of each other, and then a centerpiece. And this centerpiece slides in between these 2 tabs here. So that centerpiece basically goes right down the middle there. And then the holes across all three of them are for some threaded rod and nuts to hold the three parts together during mold loading and the compression process. And then this bottom piece was just basically to close up the mold and put in the surface beneath the tabs. And this is what those four parts look like all put together. And you can see here the chamfers here are again to put in a screwdriver and break away the components sideways in case things get stuck. And then again, you can see how these holes would line up for a threaded rod. So once we had the mold printed and sanded, we needed to develop a reliable mold release method. We had two options that were already in-house. We had Particle Paste 2 and Universal Mold Release, as well as Loctite's Free Coat FMS Sealant and 770 NC Aero Release System. So what we did was we printed out these molds and sanded them and tried to get them as identical as possible. And then we underwent the Particle Paste 2 method, which is essentially just a wax that you coat over all the relevant surfaces of the mold, and then you buff it a couple times, waiting in between buffs, and you repeat that for 4 to 5 layers. Our very first layer on the freshly sanded print was 5 layers, and then any subsequent flaps after that, the mold had just 4 layers. The process for the Loctite system, it was both components were very thin liquids that you essentially just wipe onto the surface, and then you leave it to sit for about 15 to 20 minutes. And again, repeat that for 4 to 5 coats. I believe we went with 5 because it looked pretty thin. And then, so I would say the Loctite system was definitely a longer process, just because you had to wait 15 to 20 minutes between coats rather than only 2 to 3 for the Particle Paste. But it was a lot less active time. And then the Universal Mold Release just sprays over top the Particle Paste. So once we had the mold release onto the molds and it was ready to go, we had to do the actual process of loading the mold. So what we did was we combined a hand layup technique and compression molding. So the first step of that was getting the carbon fiber toe for the forged carbon. We just took some scrap weave that we had from previous projects and pulled apart the weave and then cut it into 1/2-inch pieces to make the carbon fiber toe. And then we used a laminating epoxy. So our goal ratio was about 60-40 by weight for fiber to epoxy. And we found that by taking the part volume of the flap and multiplying it by the density of carbon fiber, and then multiplying that number with another ratio that would give us a bit of excess epoxy, because under compression, some of the epoxy does leak out of the mold. So we wanted to make sure we accounted for that. So then the process itself is you basically calculate the amounts that you want to use, and then you pre-measure them, and then you set up the mold, and you basically alternate layers of epoxy and carbon fiber toe. The most important part that we found was just making sure that the epoxy was evenly distributed laterally, and just making sure that all of the carbon fiber was fully wetted through in order to prevent any voids. So that's that picture up there. I know it's a little hard to see, but we brushed the inside of the cavity and then put in some carbon fiber, brushed it with epoxy and then put in some carbon fiber. And then on the cap piece, since it's a flat surface, we only put about 1 layer of epoxy and then sprinkled on some carbon fiber and tried to wet that all the way through. So once the mold was loaded, we just closed up the cap, pushed it in a little bit, and then put it in a table vise with these wooden shims to distribute the compressive forces across the entirety of the mold. And then you just tighten up the vise over the course of about 5 to 10 minutes, depending on how well the mold is closing. And once it's fully shut, we left it to sit overnight and cure fully. So once that was done for both of our test systems, we were able to take them out and post-process them. The Particle Paste one is this one on the left, and this one's the free coat. As you can see, the Particle Paste came out significantly cleaner than the free coat system. You can see there are a couple voids up here at the tops, and then like one right around there, but generally pretty good. On the corresponding spots on the mold, there was no epoxy or fiber anywhere. So we concluded that that was just due to manufacturing error, and that just means we didn't wet out those corners fully. But then over here, you can see this is a huge void, and this was the corresponding spot on the mold. So it basically just stuck to the mold and then tore out a piece. And this isn't really fixable. For smaller voids, you could fill it with some laminating epoxy, but that was not the case there. And then this stuff around the outside is just excess flashing. We just hadn't post-processed that flap at the time of the photo. So pretty big difference. We decided to go with the Pardo paste and UMR as it worked significantly better. And then this was the back side. You can see that just this entire part of the flap stuck to the back of this. It took a lot of work to try and get the part out, but you can see that the free coat system was not very functional. And then after that, we noticed some tolerancing issues, some problems with our mold design. This was our old mold design. It's a little hard to see, but we had a draft angle on it. It was only about 2 degrees, but it made it so that the gap between these 2 tabs was too small to fit the linkage piece that needed to go on there in order to fix the flap to the rest of the system. So we did have to go back and redesign the mold. We tried a few different iterations to try and maintain that drafting angle because we did want to have that as a fail-safe to be able to pull the part out properly. But after a few iterations and trying different things, we found that it was much more straightforward to just keep the walls perpendicular like this and make sure it just had enough universal mold release spray on it. So that's what we went with. And then another problem that we found throughout the process was that a lot of material was getting removed during sanding. So for example, on the walls of that cap piece, it didn't quite fit correctly, and for compression molds, you want to have tight tolerances to avoid a ton of excess flashing coming out. So we went back to the mold design and added a little bit of excess material on important walls to make sure that it could be sanded and not fall out of tolerance. So these are our final 4 molds that we made, or final 4 flaps that we made using the Pardal paste and universal mold release. Generally, it went very, very well. I think only one of these flaps had a little bit of a void around there, but that was easily filled with some laminating epoxy. All 3 of the other flaps did also get a layer, but that was more for aesthetics than structural. For post-processing, what we did was we just filed the flashing around here, and then sanded the surfaces with some low-grit sandpaper just to clean it up, and then coated it with the laminating epoxy. To drill the holes in, we used a mill, which worked pretty well. The pre-center drilling was very effective. And then we milled it, and then did the coating, and then re-drilled the holes through the epoxy. As for the tolerancing between these 2 tabs, 3D print tolerancing is generally not the best, and that combined with all of the sanding we had to do made it so that some of these gaps were a little bit too tight. So we did have to go in there with some files and sandpaper in order to make sure that that linkage arm fixed. Generally speaking, the process was very successful. We'll see how these work in flight, but hopefully we should be able to repeat this process if we have air brakes in the future, and maybe even apply it to other specialized parts that our future rockets may need. Thank you. Yeah.
Did you put them all together and try it out?
Yeah. They're actually on our rocket now. We haven't tested it in flight, of course, but they do actuate pretty well, yeah. Sorry? No, we weren't able to do any wind tunnel testing, but based on simulations, it should add about 380% drag to the rocket. Yeah.
I missed, how did you end up on your 60/40 ratio?
That was largely from just research of what other people were making theirs out of, and a general, sorry. We weren't able to measure the exact ratio that we ended up with, especially after like sanding and post-processing and drilling the holes. I do think based on the amount of epoxy that dripped out, we did have a little bit more epoxy than we would have wanted. That would either require reducing the amount of epoxy that we put in the first place, or making sure we didn't sand the cavity itself too deep, because that just means that the part came out a little too thick. Yeah. No, we did not. Yeah.
How did you guys land on forged carbon fiber and not something that was weaved or?
Yeah, one of the nice parts about forged carbon fiber is that it results in isotropic parts. And we weren't exactly sure, like these flaps don't undergo a unidirectional force. So we wanted something that could survive forces in all directions. And we did have some more senior members of the team used forged carbon in some of their projects, and it seemed like a viable plan. And it ended up working out. Yeah.
So, kind of building off his question, was a metal rib where like the attachment points and through the middle with a directional layup considered?
Could you repeat exactly what you mean by that? Sorry.
Kind of taking the molding process.
Yes.
How you did that, but instead of adding in the connection point in that middle rib,
Mm-hmm.
getting that made out of like aluminum
Mm-hmm.
with a standard weave layup of carbon fiber that
Mm-hmm.
kind of simplifying your mold to get rid of the connection points and that rib and replacing it with like aluminum or something similar. Was that considered or?
We didn't really consider that, largely because, yeah, we just really didn't consider that. We found that this would work pretty well as long as we got these gaps to work out. And at the point of starting this whole process and being unsure if it would actually work properly, we hadn't manufactured the metal piece to go in there. So we could work on that for any future flaps that we try to make, but for this, we just stuck with this. Yeah.
The other thing is the reduced strength by using the chopped carbon fiber a concern?
No, I don't think so. We did a few bend tests after we took the part out, and generally in like industrialized settings, I know the process is a little different, but these do yield pretty high strength parts, and they're about 150 thou thick, so they are pretty strong. So strength was not a huge concern. Again, we'll see how it performs in flight. Yeah.
What kind of speed do you think you'll be at, velocity that you'll be at when you're activating these things?
I'm not exactly sure. It largely depends on the altitude that we're getting to. Depending, these might not even need to actuate if it's around 30,000 feet. But
It's designed to, or we have programmed it such that it won't deploy supersonic, so we're confident in our data. So the fastest speed you should see is like 0.8, 0.9.
yeah. Is there a question over there also? Yeah.
You mentioned milling the holes
Yeah.
As like a post-processing step.
Mhm.
Did you have to take any care to sort of, use a milling machine with composites and not like abrade the ways or something like?
Yeah. Yeah. Our very first test piece that we made with the Pardo paste, we used that as a bit of a guinea pig to see how tight we could get the mill to fix the part in. We did end up cracking that one a little bit, so we found the upper bound of strength for that direction for sure, but it did also have voids, which makes a difference. Yeah, so we had to just be extra careful not to clamp it in too tight, and then we also had to add some welding wire underneath to make sure that the holes came out straight, because the part, it's hard to see here, but the part is sloped down a little bit when it rests on those tabs. Are there any other questions?
Back
Yeah.
to your speed again. You said you're not going to be at Mach, but the engine shuts down and you get below Mach pretty quickly. At what altitude might that be that, I mean, you said, okay, 30,000 feet, would you be at 20,000 feet or 15,000 feet?
I think our current sims are saying like we hit top speed, we decelerate. When we hit Mach 0.8,
Any more questions? Or okay, cool. Thank you.
think this would be a live stream. I think it would be a live stream. That'd be cool. At least it's recorded, you know? I don't think that AA wouldn't record it.
to launch site as well?
Yeah, I'll be at the solids pads tomorrow.
So did they give you all, like, I guess depending on the role, like, today, do you have a different role at the launch site?
Yeah, this thing is pretty easy. Right. In case
Okay.
Okay, yeah. Y'all doing all right?
Oh, you got 3 minutes, 2 minutes, if you want.
Can leave this by y'all. This is one of the parts we make. So it's really payload.
Ooh, AI.
Maybe a little bit.
Maybe a little bit less than.
Additive.
Yeah.
It's additive. Ooh, you need another focus ring.
Where'd you put that?
I mean, I can stand on it. Thing's not breaking. Survived, what, 27 Gs and then hit the ground at 100? A minute. Do you need a mic check?
Oh, you're good.
Okay. I think we're ready.
Yeah, let her rip.
Okay. Alrighty, so our group for this podium presentation, we did machine learning based additive manufacturing for lightweight aerospace components. Just a little bit over our project. We're going to go over just a small background, problem, sort of this new machine assisted design philosophy. We did some computational analysis as well as our experimental analysis, and then we'll go into results and what we've gained and gleaned from this project.
So for our background, we're the Space Cowboys rocketry team. My name's Neil Sanpara. And so one of the problems that teams regularly face every year is the problem of mass. So we want to minimize the mass of our structural components and try and maximize our valuable weight. So what we specifically need for a lot of these structural parts is a high specific structural strength and a vibrational strength. A lot of times vibrational analysis kind of left out. And that's, I think, still a very important component, especially when you have a rocket that's going 27.5 Gs at Mach 2. So one thing that we've turned to in the recent years in the aerospace industry, or just in general, or looking into, is additive manufacturing. So a lot of rocketry teams here at IREC use a lot of additively manufactured parts. But specifically what we wanted to look at was additively manufactured metal parts. It's kind of a new paradigm. And so what that allows you to do particularly is topology optimization. And by topology optimizing standard parts that would be designed by a human, you can get parts that are even higher in specific vibrational and structural strength.
So one thing that we've looked at, the first word paper was a Goddard paper, 2022 from NASA. And they designed this part for a satellite mission. And so this mission had a small little bracket, and so they had human engineers in a loop versus an AI. And really it's just a machine learning algorithm that is just iteratively designing. And so what they wanted to do is have a extremely small part. And so at those low mass values, the humans were just not able to compete. The design took too long. And those parts were nearly up to from basically 6 to 10 times the specific performance of that part, which is really incredible. So we saw these results and we're like, hey, is this repeatable? Is this something that we can actually do? Is this something that's actually financially viable? So we sought to look out this. So our approach, back to Neil.
So sort of our approach for this whole process was first we need to identify some parts that need optimization. So one of the things is you have to choose a part that essentially might be high in weight if you're traditionally designing this part, and see if you can use this process in general. So the second thing we need, so the thing we needed to do was meta-optimize and design with machine learning, and we'll actually talk more about that procedure in depth later, some of the inner workings of that. And then what we need to do is actually validate those results, especially since this is additively manufactured metals, and you're using a new topology optimization method, which might do some odd things depending on your constraints and how you're building out the part. So we need to like actually physically validate this. So 3 things that we actually did for this project were vibrational testing at NASA Marshall, structural testing at the Center for Advanced Vehicular Systems at MSU, and a real-world rocket launch as a part of our Helios flight vehicle test launch.
So yeah, before we just go into what we've designed, just some small limitations. This is a limited set of parts that we wanted. We wanted to keep the variables as small as possible. We did have some extra parts that one of those we've shown to you, but we did not do, or at least we're not going to show the results here just to keep the time to a minimum.
So the primary part that we chose for our Helios flight vehicle to test was essentially a thrust transfer structure that is used within the boat tail of the vehicle. So last year with our vehicle dataless at IREC, we had an issue where the boat tail actually popped off. And fortunately that year we couldn't even have flight test before that. So that was actually unexpected. It was the first time we were doing a boat tail. And we had learned of this thing called the Krushnik effect. So we wanted to minimize the nozzle recession within the tail cone. So we designed this thrust transfer structure. We call it the aft truss, and it's a removable structure, and it has 2 interface points, one for the Aeropack rear retention ring, and one onto the thrust ring that is mounted to the rear of our rocket. So there's 2 parts that we designed. One was an engineered truss, and so this is designed by a human using some good rules of thumb for actually designing a part. And then the next thing that we wanted to test was the topology optimized part. So we wanted to basically compare the 2 and see how they performed with respect to each other.
So just explaining a little bit behind what we use machine learning for. So we initially got the geometry. So we built that engineered part first, and then from that we were sort of informed the geometry. We know our input loading condition. We used CFD, we used FEM, we used other analysis techniques and got the worst case loading for some of these parts. And so we knew exactly where that was going to come from. And then we transferred that step file over to the Izanagi machine learning model. So this is a kriging-based model. I'll explain in the next slide a little bit more about it. But in the loop, it picks the sort of design variables of the problem, and then it will train these on our HPC. So we train these with our clusters. And it will do solution solve. So you'll basically get, it's a data-driven surrogate model. And so then it builds sort of a latent space of what the real world actually is. And then from there, you can optimize that. And automatically, through that process, we get the best design. And we go ahead and print that on the Renishaw AM400. And we print it out of ALSI 10MG. The reason why we chose this material was because of its cost effectivity. It is one of the cheapest metals we could buy. And we're looking for sort of, that was one of our major constraints, so we want to make sure we could actually afford it. And then that part gets printed. Then we post-process the part, so any sort of actual holes we need to do on the part. And then we actually then verify it with what's called a digital twin. So for those of you that don't know, a digital twin is some model that is in the real world, but also in some virtual world. And basically what you can do is if you can verify via the real world the testing, and then compare your virtual results to that, you can sort of build virtual experiments and spend less money. So essentially, Boeing has been doing stuff like that, where they're switching out of wind tunnel testing for some of their planes because you can do all of the stuff that you can do in real life with CFD. And it only makes sense if it is more cost effective, which it has been with recent computational power improvements. So machine learning model is quite simple. It's a regressing Kriging model. And so Kriging basically builds a Gaussian set of functions. It's CPU trained, so it doesn't really need that much extra processing power like of GPUs. And it uses scaled Gaussians, so a Gaussian curve is a normal curve. And so many like small dimension variables typically follow that. The loss also includes penalties for mass, as well as designs that are way too out of spec in terms of stress. So it actually does take that into account when it's optimizing. It knows that the parts that perform very well in stress, but are like giant chunks of like bricks, are not going to actually perform well in a rocket. You need something that's efficient, something that has less mass, but also very, very high stress tolerance. Oh, come on. There you go. So going into our computational vibration testing, so we did pre-test analysis before we got to NASA, and we used ANSYS free and fixed modal. And so we tested these two parts. We're comparing the engineered left, topology on the right. The first free mode, as well as the specific first mode, is better for the optimized part. So that was our computation results going into NASA. Then we went to actual NASA. So we tested in the ET-73 West Vibe lab. As you can see, the parts there are two accelerometers on the sort of test fixture. And then there is one on the actual part itself measuring the response. So we can get the sort of control versus response, do some statistics on that data. What we did was we did pre-sine, random, and post-sine. So a pre-sine is you're basically going to sweep up from 2 to 2,000 hertz. And you do the same thing on post-sine. The random test is the real test. You'll put a lot of energy in. For us, it was about 0.25 G squared per hertz. And so you just take a bunch of energy, you get all the modes at once, which is really nice. In the post-sine, you're just checking to make sure that nothing backed out, that the part didn't delaminate. And that was one of the concerns. Do the additive manufactured parts delaminate? So we performed a lot of tests, but I have a video for y'all of just one of these tests. As you can see, it's not super crazy, but it is cool. We got a lot of data out of this test, and yeah. It's pretty boring, so I'll just skip through most of it. There we go. So just a pre-sweep, we got our sort of response there. Those red lines basically are the control response, so of course you're going to have some that go above that. That is pretty normal for a part. That's the control error bounds. And so we didn't find any detectable modes in the first 22,000 hertz. Same if we did random, so showing random. We don't really see any detectable modes below 2,000 hertz. We knew that from our computational results, that wasn't going to happen. So we've pretty much verified that these parts, without a doubt, are not going to have any issues on the rocket in the current configuration. And what's really nice is that the topology optimized part performed very similarly in this frequency band, but at less weight. It was 25% lighter. So we thought that was really cool. And now I'm going to pass it on to Neil to talk about our structural testing.
Okay, so the next thing we did was actually do structural testing on these parts. So for the first step, we actually did some computational analyses prior to actually physically testing the parts. So we used an antistatic structural instance for compression simulation. And so what we did was we applied a fixed boundary condition at the bottom of the part and a distributed load at the top. And we applied an axial load incrementally until failure. And so we found, or until yielding. We found two yielding loads. So for the engineered truss, that was 39.7 kilonewtons. And for the top-op truss, that was 52 kilonewtons. So if you go back one more slide. So for experimental testing, we had sort of a short time frame. So we were trying to look for a machine to use to actually test our parts. So we ended up settling for the Center for Advanced Vehicular Systems, the Additive Manufacturing Lab. They had a compression fatigue test machine, which is the Instron Model 8850. And so what this machine does is it keeps your strain rate constant as you're testing the part. And then the machine automatically starts backing off when it detects a change in the stress gradient. So this is just the strain versus time curve. Nothing really to see here. It's just a constant strain rate for both parts. So on the left engineered and the right top-opt. But what's interesting on the stress curves is that you actually see on the topology optimized part, it reaches a much higher peak loading. So you see about 40 kilonewtons there. I mean, megapascals, sorry. and about 36 megapascals for the engineered part. And while also keeping a lower mass for the topology optimized part. Okay, so for test launch 1, so this is actually our flight testing portion. So for test launch 1, we actually ended up installing the engineered truss, and this is the one that was actually flown in my hand. So the truss was installed pre-flight with the aft retainer, and so what would go over this structure right here is the boat tail, and so it's actually a removable boat tail. So some of our flight expected loads were primarily from the motor. We had about 1,697 pounds of peak thrust, about 330 pounds of max drag for a total max loading of around 2,027 pounds. The reason we can also we can say that this could be our peak loading is they occur at around the same time as well. Well, as max Q. So about 1,200 pounds of average thrust for 4 seconds. So for our results, we had successful post-flight results for the engineered truss. We saw no damage resulting from the flight loading. So visually inspecting it, it was pretty good. And we could actually reuse this part in assembly and see that the motor actually fit just right as well. So for IREC, we're using a second version of the truss that Austin is holding. And so that's on the right, as you can see there. And that's what we're going to be flying tomorrow, hopefully. And so topology optimized parts, they provide some unique benefits. First of all is the lower mass. So the topology optimized truss, the first one, was 0.61 pounds, while the engineered one was 0.88 pounds. So this one's 0.88 pounds. And not only that, you're also achieving higher specific modes and strength.
So, yeah, just a quick summary of what we've sort of found out with this project is that, you know, they exceeded our expectations. We weren't really expecting this to work as well as it did. Of course, cutting into these parts, doing some post-processing, you could see that it was actually aluminum. It wasn't just some mystery material, which is really nice to know. We also wanted to actually do the vibration testing because that was something that was pretty concerning, at least for, you know, additively manufactured materials, composites, multi-laminates. We just wanted to make sure that was going to work. So in general, we saw the machine trust averaged over all of the performance metrics, performed similarly. So no significant change, but it was 15% reduced mass for that first truss. Of course, the block 2, block 3 have gotten lighter, and they have also gotten stronger. This is because we've added a little bit better methodology behind our machine learning, and it's gotten a little bit better. So I think the real cool stuff is the impacts for sure. So if you have a part on some rocket or some, let's say like a jet nacelle or something that is taking a lot of force, but also taking repeated cycle loads, you could potentially make that part up to 7.5 times stronger. So that is mirroring the NASA data. They said that they were able to get almost order of magnitude improvements on some of these parts. So the reason why that's important is, of course, you're not testing most aerospace parts to failure when they're actually doing their job. You're keeping them low, and then you're making sure that that's not going to exceed a fatigue limit over the entire lifespan. So it will increase the fatigue life. That is just a matter of fact. The other thing is that, especially for some really tough parts that are complicated, especially if you have multi-fluid interaction, some internal structural part, you automate that process if you use machine learning. And so we found that we've massively saved on time and design for something like this. In terms of the future, we're looking out towards some further testing of these parts. Another thing is we were trying to design some air brakes, which is really nice. So especially for an air brake system, you need to have it lightweight. You also need to be strong for all those different loads. And then we want to do fatigue and sort of more in-depth quality control. So X-ray, tomography, stuff like that. As soon as we have access to those machines in CAVs or other facilities that would like to partner with us, we'd really like to look into that because we want to see what's going on at the micro scale for sure. Yeah, we'd like to thank sort of all our professors that have really helped us out with this project. Of course, ACI, CAVs, the High Performance Computing Collaboratory for lending their resources, and of course NASA Marshall, AT73, y'all were super cool. Thank you so much for letting us test. And yeah, I'm gonna ask, does anyone have any questions?
Did you have
Yeah, so
Did you knock on their door and say, hey, what
so I worked at Jacobs Engineering. I think they're like Adventure now, and so I worked like SLS, and so I wasn't in that same area. I was in like dynamic testing, but I asked just out of the blue because you know, just seeing, and they were like, hey, yeah, we really want to use it as like a guinea pig group for like outside people testing this, and so we got really lucky with them. So.
All right, so I'm going to go back to the beginning here.
Yeah.
The truss part is you're designing this because to hang in the boat tail, or is it?
To actually bring the nozzle back at the end of the tail cone, so that you don't have any exhaust interaction effects inside the actual boat tail.
It's basically a
Just
nozzle
a low
extender.
transfer structure, essentially.
Oh, I see. And so that is your nozzle on the back here.
Well, what you would put in a motor, so that's the aero pack at the end, right? So the rear retention.
There we are. Yeah, there's the
That's
nozzle.
right there. That shattered there, but
It's after flight. It's pretty normal.
a little off. So the boat tail goes over that whole structure.
Yeah, I was going to ask you about your vibe table, but it looks like it was acoustic.
It was not. It was it was actually like a electrodynamic shaker. I think. Yeah, electrodynamic shaker right there. So we used T2000H and V.
So you get 3 X, Y, and Z.
XYZ did all those tests. Yeah. For these parts, I mean, they're very short and stubby. We were expecting to not have any, significant issues, but especially for parts in the future that might be like taller, that would be something very interesting to see.
What was very interesting is actually this truss here, the Topology optimized one, for compression testing. The only place it failed was where we actually purposely put holes for this vibration testing on the sides. So it was kind of a testament.
On the dip on the right-hand side, you go outside your, what is that, 6 dB, 3 dB?
Yeah.
It goes outside, no big deal because it's so high frequency.
Right. Yeah.
And what alloy did you use, and did different alloys have any different results?
Yeah. So we used ALSI 10mg. It's closest thing to 6063 I think that you could probably get for an additively manufactured material. The one thing is definitely cost. Like this stuff is still cost limited. Of course, because it's powder bed, if you want to print anything tall, you got to fill up the entire bed of material. And so, of course, you have to purchase that powder, to get up all the way tall for some of the tall parts we had printed before. For short, stubby trusses, it still doesn't matter. The cost per kilogram is getting closer to extruded. You're still never going to beat simply, CNC'd parts or something like that. Yeah.
Did you do any dog bones with it?
This is definitely, I guess,
Dog bones.
Yeah.
Yeah, so dog bones, we didn't do any specific dog bone testing from this. We used the internal sort of calves testing, and we looked at the results in their paper. If I had more time or more financial resources, I would have wanted to do those to test different orientations. But from their testing, it didn't look like there was a significant change between either Z or XY, which is really, really nice.
Definitely probably a technique for more specialized parts. Any other questions from the
Do y'all want to I might pass these around if you guys want to look at them. But yeah. So that's the payload top shelf. So if you've seen our payload, it's got sort of the top shelf that's combining everything together. That's in there. And we designed that sort of also to fit a specific mass. So that was actually a different sort of problem. We weren't trying to super light that weight that one. We were trying to actually fit a mass target. So yeah.
The verticals here are the way you get strength with lightweight?
Those are actually supports. That part wasn't actually like post-processed just yet. So the supports are still lingering on there.
Oh, you would cut all these out?
Cut all these out. Yeah.
Okay. I thought, if you put little columns all the way through it.
Yeah. I just be careful. There's might be sharp on the edges. Oh, yeah. Reagan, question?
I remember at the beginning of the year we had done some research, or looked into a little bit into welding in this material. Were there any
So that's one thing that we're going to be doing in the future with the air brake system. We want to test the weld. We have actually tested welding with this, and I forget what filler it was, but it does weld. That's the other useful thing about LSI 10MG. You can weld parts like these. So parts that can't fit into the bed, you can weld to make larger. Of course, you know that you have to be careful with your strength and do your math there, but yeah.
How reliable was the printing? Did you have any print failures where parts came out misformed or failed halfway through?
So Neil, you want to talk about just the ones that failed?
Yeah, there were definitely some failed parts where I guess so. Like a lot of the trusses, some of them were having issues with. I guess you were having a lot of voids and not enough powder filling.
Yeah, there were some machine issues, and the machines are, you know, it's not just like a CNC where you could probably run a CNC in a desert or a jungle or something. It would actually work. The powder, 1 week in the lab, it was a little humid. They started printing with it, and it failed at a certain point, right? And you just can't do anything about that. But as far as like the final part, we didn't do like tomography or it's called metrology on any of them. But whenever we wire EDM'd, like we made sure we take the good measurements. Like they're worth, like at least for this size of parts, they're within like within 5 thou, which is really nice.
Control where it's necessary is like material handling, like especially with humidity and stuff. Like the lab we were using actually had a whole process for actually, you know, basically getting rid of the moisture in the powder.
Yeah, yeah. Question back there?
Given that you can modify like what the penalties for being AI model is, would it be possible to make it where instead maybe for say like a low mass, you could like have it a bit priority for a low cost?
Yes, that is 100% possible. Because the objective function pretty much just controls everything. Low mass, low cost. You could do something where it was like it would penalize designs that had a lot of supports. Something that would like waste a lot of powder. You could do that. Also for like multi-material optimization, which is it's up there, but it's possible. Is that you could optimize for a part that was extremely low cost, and so it would use cheaper materials in some certain areas that didn't need that strength, but in stronger stuff like Tie 6. Okay. Alrighty.
Can you go? Okay. Okay, hello everyone. My name is Henrique Vieira Perez. I'm the coordinator of the aerodynamics department from the structures department from ABC Rocket Design, the team 302 from the IREC to 1025. The college is Federal University of ABC. And here we're presenting the nose cone manufacturing using vacuum lamination technique. Introducing the introduction. The project RC means is designed to the presentation, right? For the nose cone fuselage made out of fiberglass, it was made to get a good strength radio, good strength rate, good weight strength radio, and a good aerodynamics performance. We had some troubles about the manufacturing, the traditional manufacturing is a hand layup method, so we changed a little bit and innovation with this one. Why this geometry of nose cone? We used, we run a few simulations in CFD ANSYS, and we run a few simulations in Power Series and Hack Series, and we found out that the results of Hack Series was a little bit better. So, and even though the Rack series, we use the von Karman series to optimize aerodynamics for the subsonic flight conditions. So the nose cone is 35 centimeters height with a Hack series, the von Karman series, right? And made out of fiberglass. The material selections, we could choose about, we can choose the options we had, right? It was fiberglass, carbon fiber, and aluminum or carbon, aluminum or steel. And the steel, the metal over here, we did not use it because we would add so much weight to the rocket, so we chose for lighter materials. Carbon fiber was a good option. It has a really good strength. So, but it's too expensive, and it came out of our budget. So we choose the fiberglass. Fiberglass has a little good points to use in this project because all of the fuselage are made out of fiberglass, so we already know how to use it, and how you're used to it, it's made easier to promote new methods, right? And okay. And why innovate? Okay. Yeah.
So hello, my name is Lucas. I'm the marketing coordinator and also part of the structure department. So why innovate? So first we tried using a manual fiberglass lamination that is also called hand layup way. And it's a simple way and cost-effective way. And we don't need to use a lot of equipment to do it. But we faced it with a lot of challenges and a lot of issues during this process. First, we have a problem with the complex geometry and curvature. So it's difficult to have a uniform distribution of the resin during all the nose cone. So it's difficult to do that in a complex geometry. When it's finished, the nose cone has a lot of air bubble here. It's not good because it get a little bit wicked. It's not a strong nose cone. And another point is that even if you don't get trouble with the other 2 points here, you have to have extra time of work because you have to do a rework or you have to spend a lot of time sanding it. So we decided to find another way to do it, and this way is the vacuum solution. We use the vacuum bag to do it. So the points here that we see that is very good for us is that First, it eliminated the bubbles, so now we don't have any air bubbles here. So it's very good because it's a really strong nose cone that we have. Also, we can now have a uniform distribution of resin, so it's much better and much easier to do it with the vacuum. And another really great point is the material optimization. So we don't have to put a metal tip on the top of the nose cone because it's already really strong, and we don't need to put a metal thing here to help us because the fiberglass with the vacuum is already really strong. So, and the last point is that we don't have to spend a lot of time on doing some rework or sending a lot of things to make it better or make it perfect, you know. So, yeah.
Hello, my name is Isabella. I'm Structures Department Coordinator. For our actual vacuum lamination process, we divided into the pre-lamination and the actual lamination. For the pre-lamination, we start by using a CAD-based geometry extraction that we printed on A3 sheets and later used to cut out our fiberglass into our desired shape with a 20 millimeters margin. And we also prepared a mold using 4 layers of release agent spaced in 20 minutes between each layer. And then we start the actual lamination. For the lamination, we impregnate the fiberglass with a set amount of epoxy resin and catalyst that is defined by the mass of each fiberglass layer. And having that amount set, we pass it around all the fiberglass, close it, and use a spatula to make it even coated. And after all, we use a bipartite mold, a 2-part mold. So we put 2 layers at the same time on each side and then close it up. For this project, we use 8 layers. And after all layers have an even coated resin on top of it, we add 3 special sheets. The peel ply that helps as a release paper, the perforated film that acts as a way for the resin to go through, and the breather fabric that helps to absorb the extra resin that we have. And after that, we close our mold and screw it up to secure the position of the fiber. So for this type of lamination, we have 2 different ways to do it, with 2 different types of molds. The first type that we tested was a mold using gel coat. We based that on a lamination process using our automotive in Brazil that we have in Brazilian stock car. And we used gel coat to make a mold to use it as our nose cone. We start by using a 3D printed counter mold to put the gel coat on top. And after that, we let it sit for 1 week to start the lamination. Okay. After the mold is ready, we apply the fiberglass on the layup using a spatula to confirm that we can manage to get this little section right, since it needs to be a little degree here, 90 degree. And here you can see better. And after that, we just close it up and put into the vacuum bag. That let it sit for 5 hours with vacuum and then transfers into a 1-week cure process.
Okay, hello everyone. I'm Rafael Salinas. I'm a member of the Structures Department. And after all of this, we decided to move on away from the gel coat. Okay.
Sorry. Using the gel coat, we actually had a good structure, but we had a little bit of problems using a lot other parts. So as you can see on our nose cone, we have a book head inside. But since our gel coat wasn't really exact on the same measure on both sides, we ended up having a little bit of an ovalization on our nose cone. So that made it really difficult to continue with the project. And we had to change a lot of things. And unfortunately, we also had a problem with the curing process. Our fiber didn't really didn't bond with the resin, so we could have a delamination problem if we continued with this method.
Okay. 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 We decided to confront our challenges and get rid of the gel coat, and instead we decided to use a printed model that we printed ourselves. It actually worked much better than the gel coat. First of all, the most important thing was to choose the right material for it. We first tried to use ABS plastic, but it was causing a reaction with the resin. The made it get warped, so we changed it to PSL, PLA. I'm sorry, PLA, and it worked much better. We also had to make some improvements on the CAD because the measurements of the real life fuselage were not exactly the same as the CAD measurements. So in order to fit the nose cone well, we needed to have some changes in the measurements of the mold. So we also had to split the mold into parts to make the demolding more efficient. So we could just open it and take the part out of it, and it worked really well. Okay. We still had some difficulties because the 19 degrees that we needed to have here is quite difficult to get in the vacuum lamination because it can get there's the thing called bridging. That is when you have a corner, you can really get a corner in the vacuum lamination because it gets a curvature in the fiber. So we tried a lot of different things to solve this, and I think we got a good result, but we still need a lot of work to make it perfect. We know that, but it's a really good process, and it can be solved, and we are looking forward to make future research to make it look even better. Okay. The project IREC showed us that even with limited resources, rocketry can still achieve some pretty innovative design improvements. Yeah. Here are some key lessons we learned. One of them is that the vacuum bagging is really better than the hand layup. You get a stronger and more reliable component. The second, the fiberglass. The fiberglass remains being the best material for us. It's more reliable, it's more adaptable, and it gets the job done. Third, the 3D printing really sped up our prototyping process, but we have to take care of the material we use because, as I said, we are trying to use ABS plastic. It didn't work, then we changed it to PLA. Okay, just finishing my speech. The process really had a positive outcome. Yeah, in the end of the day, it wasn't just about making a nose cone that was functional. It was about challenging ourselves and learning from our mistakes and making improvements for engineering as a whole. Thank you, and we can answer some questions now. I think. Do you have a? You have a question? Okay.
And you guys said you did like 4 tries or something, 4 or 5 tries.
Yeah.
I just tried to do like one vacuum bagging and the other one just hand
Yes, our very first try was actually a normal hands layup method, and we used a inside mode, so we laminated outside of it, and it didn't quite work because since it has a curvature here, the fiberglass didn't actually stick to the position, so it kept falling up a little. And it was very difficult to maintain it on place to do all of the layers that we needed, so we kind of ended up scraping that and tried already the vacuum lamination.
It was also really hard to get a tip in the manual process. So the vacuum lamination, I think the best improvement that we had with this is that we can get a tip without having to use the metal part, like you said. Okay. Does any
So you talked about some of the work you did selecting the bicarbon style nose cone. Did you consider various height ratios, or was it kind of a set limitation based on available sources like a 3D printer and stuff like that?
Yeah.
Was limited things that we could do, so we made the best we could with what we had.
Are you worried about like aerodynamic heating or heating out in the desert with your epoxy system, melting? Have you post-treated it? I know you can post-treat with ABS. I'm not too sure whether you can heat cure with PLA.
What? Can you repeat, please?
Have you post-cured your composite? So is it autoclave or put in an oven?
Oh, no. It's just, we could use a woven, but doesn't this, no nose cone. So it is just stay on the ambient temperature. Any more questions?
How did you apply the vacuum bag, like to the mold? That process.
We use like two molds, right? They fit together, and we put the vacuum bag inside of it, and we had a little trouble putting it right on the end of the nose cone inside, but how it is laminated for the external part, it had a good surface on the outside, and inside it has not a really good surface. So inside here is not very good for the surface, but outside is really good. But we was like one mold like here and one on here, and we put the vacuum bag inside and recovered it like this. So it's coming inside like this and outside.
Yeah.
So yeah, I think you understand. Okay, sorry.
What sort of testing did you do to prove that the vacuum bag's nose cone was stronger than just the wet layout?
Oui, skip pas? Attends, ok. The test that we did is the fact that we actually tried to make the manual lamination and we just couldn't get it done right. So for the purpose of rockets, it didn't work at all. So for us, for our experience, it's really stronger this way. It's really the tip is really sharper this way, and it has the shape that we need. So for the purpose of a rocket, it's stronger than we had before.
In the other tries we made for making that, we had a lot of bubbles and a lot of bubbles and a lot of the lamination, and all the tries we made. So this one hasn't it. So we just assume that it's really better and stronger.
About how many layers or how thick is the layup of your nose cone?
It has 8 layers. Yeah, it depends on. What? It's 3 millimeters. Millimeters. It's 8 layers, or 6 layers depending on the geometry of the of the fiberglass.
You've spoken about your problems with bridging. Have you thought about what you would need to do in order to be able to integrate this nose cone with a rocket? Sorry? You've spoken about
Okay.
So we did our best here to maintain as close as possible to the 90 degrees, but to prevent it from aerodynamics problems, we are planning to add a tape on top of it, a silver tape, orange, to match our rocket. And that should solve the aerodynamic problem, but the securing part, this part doesn't actually affect it. It is just bolted here, so it's totally fine to have it not at exactly 90 degrees.
There are some things that we can do in the illumination process in the future to try to make it better. Like when you apply the vacuum and after you completed the illumination, you can put something here to press é uma palavra certa? To press the lamination against the wall of the mold, so it won't it won't make the curvature. It will stick to the wall, and it won't release easy in the vacuum. Is something that we'll maybe try to do in the future to improve the nose cone.
Other thing we thought about is like, instead of making just the nose cone in the lamination, make it like a nose cone with a bit of fuselage, so it doesn't have to head the 19 degrees. It can just smoothly go up to and be a fuselage with a coupler over here. So this probably should solve this problem. We used the same amount of layers of the fuselage. We made the traction test with the fiberglass using in the fuselage. So we used the same result for to choose the numbers of layers in the nose cone.
Any more questions? No? Okay. I think that's it then.
Okay, I think then we're good to go. Yeah, thank you for a chance to present our work here. I'm here from the Technical University of Munich today to present our work on the design and process development of a multi-shot CFRP fin can. In general, the issue was that we built a two-staged sounding rocket this year, and therefore obviously we need the fins to stabilize the rocket during the flight and keep it stable throughout the whole flight. Therefore we came up with a novel design for the both sustainer and booster fin cans. They should keep their vehicle aerodynamically stable, as already mentioned. Also, for the sustainer, they should include the staging mechanism, obviously withstand the structural loads, and all this while being as lightweight and as low drag as possible. Last year, we had a design consisting of one body segment, 4 fins, 8 fin holders, then one additional boat tail that included the staging, and a lot of fins, a lot of rivets. This year, we only have one fin can that combines all those functions. Here's a more detailed cross-section view, how the fin can, in this case the sustainer fin can, is set up. I will focus on the sustainer fin can during the presentation, but the booster fin can is first of all right here, and second of all more or less the same. So we have 4 individual quarter shells here. They were laminated on a PI mold, but more on that later, and then cured in autoclave. And this means we had 4 sections consisting of 4 quarter cylindrical sections with 2 half fins each. Then those 4 individual sections are bonded together and reinforced by 2 ribs here. Those ribs also center the motor through the circular cutout in the middle. Apart from that, to get as sharp leading edges as possible, we had forged carbon inlays, leading and trailing edge as well, to structurally bond the individual quarters even better together. There is one additional reinforcement ring here. And last but not least, there's the staging interface here. So 2 rings basically to center the sustainer stage with respect to the booster. Obviously those are missing on the booster stage. Yeah, and one thing I actually forgot is the foam. So we foamed the fins afterwards, so they're even stiffer. There's a more detailed view on the staging interface, on the staging ring of the sustainer fin can. That's machined from aluminum. Here you can see that on the over the bottom surface right here, the thrust of the booster is transferred into the sustainer stage. Also the circumference out right there is used to center the sustainer with respect to the booster. Then there is one dowel pin in there to align the stages rotationally. And we have as well the PCB mount to connect or to mount the interstage PCB to be able to connect both stages electrically. And also there is one surface right there that transfers the sustainer motor's thrust into the remaining structure. For the main purpose of the fin can is obviously the aerodynamic stabilization. Therefore we did some deep analysis. So the requirement is to have a stability larger than 2 in calibers throughout the whole flight. At the same time, we wanted to minimize the drag, more specifically the wave drag, and therefore we used semi-empirical methods, and in the end also CFD analysis. As you can see here, you can very nicely see the transition from the laminar to the turbulent boundary layer, and then also the interaction of the flow with the fins, and then here the shock system developing around the fins at Mach 2.5. From a structural point of view, we had the aerodynamic fin forces, obviously, those were around 850 newtons. Then, apart from that, we have the thrust forces and the staging loads, since, as I already said, the sustainer fin can also includes the staging mechanism, and therefore sees a rather large bending moment during the erection of the rocket on rail. This is one of the already mentioned quarter shells. So as I said, it's the cylindrical section in the middle and then the half fins on each side. For the booster and the sustainer, there resulted two different layups, since the sustainer had also to transmit the thrust loads. This is not the case for the booster fin can. However, in both cases, we have only one layer of CFRP going all around. So the majority of the fin is only one layer of CFRP. Then, in the case of the sustainer fin can, there are two layers, plus minus 45 degrees. Those are the red ones. And then one additional plus minus 90 degree layers to cover off the reinforcement layers in the middle. That goes up until here. That's the case for the sustainer. For the booster, we only have one plus minus 45 degree layer in the middle, so it's plus minus 90, plus minus 40, 090, sorry, plus minus 45, and then 090 again. The mentioned ribs have a thickness of 5 millimeters, and with that, we encountered rather high factors of safety, which is good for us, and also was kind of the goal, or not kind of the goal, which is good for us, and we are happy about this because some assumptions had to be done, and the structural integrity obviously will not be exactly like in the simulation, but we are confident that with the assumptions and the factors of safety, everything is perfectly fine. We did tests, tested the bending moment, and everything was perfectly fine. Yes, now to the manufacturing of the individual components. The quarter shells here, you can see the mold of the individual quarter shells, as I already said. They were 3D printed actually from PEI, carbon fiber reinforced, milled, sanded, and then sealed. So, and then we laminated to those into those molds with Cycom 977-2A CFRP pre-preg, and cured at 180 degrees for 3 hours in the autoclave. Afterwards, the resulting parts, this is how the parts looked after, this is how the parts came off the mold. Then they got CNC trimmed to get rid of the excess material right there. And this is how the trimmed quarter shells and the mentioned ribs looked in the end. The ribs were water jetted from the 5mm CFRP plate. The mentioned leading and trailing edges were not laminated but fiber pressed. So this means we made one mold from Uriol, and so we milled the mold from Uriol and then pressed the fibers into this mold. So in the end we had the forged carbon fiber inlays. The reinforcement ring that was mentioned was laminated, wet laminated on a 3D printed mold, and then glued in the fin can. Staging rings were cut and lathed to the rough dimensions, then glued to the remaining structure, and afterwards precision milled, so everything is coaxial and centered. For the assembly of all the individual parts I mentioned, we built an assembly jig made out of 3D printed plastic, PTG, and reinforced by aluminum profiles. This is how they're looking. So that's what we've already seen. The assembly jig here with the PTG parts, aluminum profiles, and then you can assemble 4 of those units, let's say, together, and then you got the assembled fin can inside the assembly jig. That's again the assembly process. So we had the first quarter in the assembly jig, added the ribs, added the second quarter and the CFRP ring in the middle. Then we added the third and fourth quarter, bolted everything together with the assembly jig and cured this, so cured the glue. Afterwards, we opened up again the assembly jig, took the fin can out, added the leading and trailing edges, put it back in the assembly jig, cured it, and as a last curing cycle, we added the staging rings. That's the result of the fin can after the first curing cycle. So you can see the leading and trailing edges are still missing, but the fin can is holding together. All in all, we saved almost 50% in weight. The wave drag got significantly reduced, and most importantly, the number of parts got reduced, so the number of individual parts got reduced from a lot to only one individual part. That's the fin can in real life, and now I would be open for questions. So we had here, we had here the which glue we used. It was Loctite 9394. Yeah. And then we applied it here in between the ribs and the fin can, and then also in between the CFRP ring that sits right there in the middle. You can see it on the picture. Yeah, exactly. Yeah.
So I noticed that kind of each stage has a different fin design. Is there a reason behind that? What kind of went into creating?
Yes. Yes, this is due to the different Mach regimes we're encountering. So for the booster stage, we are subsonic through the whole flight, even though we reach the transonic region. But for the sustainer, we go well into the subsonic, into the supersonic regime. This is why the leading edges are further swept. Yeah, to keep the subsonic leading edge.
Well, I noticed like y'all used trapezoidal of the booster, but more of a clipped delta of the sustainer. So that's just, based on which range you're operating is the main focus behind that, right?
Sorry, can you repeat?
So, based on which range you're operating in, super or subsonic,
yeah.
is
Exactly. Exactly. Yeah. Yeah, yeah, thanks for the question. I remember that I accidentally skipped this part. Yes, so this got glued together, and then it looked like this basically. Then we added the edges, but there's no foam inside yet. And after everything is glued together, all the inserts are in, we poured in the foam from the inside to get the sandwich structure in the end to increase the stiffness. Yeah, definitely. But we feared that the foam, or that it's really hard to get the thickness of the foam right in the beginning. And if the foam is too thick, obviously the fins are not perfectly bonded together. There are gaps. If the foam is too thin, then its foam is not bonded to the carbon fiber plies. Therefore, we decided to do it afterwards. Fine. Okay. Yeah, then thanks for the attention.
Okay, so hi everyone. Thank you all for being here. My name is Victor Bonilla. I'm a senior in aerospace engineering, and I'm part of the special project sub-team of the Sun City Summit rocket team from the University of Texas at El Paso. As a team, we not only focus on building and launching our own rocket, we also focus in improving the skills of the students, of the members, and to grow as professionals and as engineers. So that's why during the last couple of years, last couple of months, we've been doing some research so we can bring new ideas to the aerospace field. So that's why we did a development and testing of an innovative multi-layer plate deployment mechanism for precision altitude control. So this is also known as the MLPD air brake. But what is an air brake? So as you know, an air brake is a mechanism that will control the altitude of, in this case, our rocket by basically improving the drag force of the rocket, so this will decelerate the velocity of it. And there are two common air brakes that I have seen around here. The first one is the sliding pop-out plate, or also known as the sliding air brake. This one, as you can see, is a simple mechanism. It might have around 2, 3, or even 4 fins. And it's pretty straightforward, like the fins will pop out of the air brake, and as I said, this will control the drag force. And then we also have the hinge fins, or also known as the umbrella system. As you can see here in the pictures, it's pretty straightforward as an umbrella. Like it is stick together to the body tube, it's aligned with it, and then once it opens, again, as I said, it opens as an umbrella, and this will start to decelerate the rocket. So there are some common challenges that we are trying to either to not resolve, but get better results for our rocket. Some of the challenges, first for the sliding pop-out plates, this one is kind of limited by the rocket diameter. So this means that if the diameter of the rocket is pretty small, then the surface area of our fins, of our plates, will be pretty small. So again, if the smaller the body tube, the smaller the surface plate. So if we don't have a good surface area, we won't have a good drag force in order to decelerate the rocket. And then the other, for the hinge fins, again, or also known as the umbrella system, we need to cut a large area of the body tube. As you can see, that yellow square is the area that in this case, in this example, we need to cut off the body tube. So this might compromise and damage the structural integrity of our rocket. And we might have some problems with the CP, with the CG, and we want that in our mission. So what are we trying to solve? What are we trying to improve? And why am I saying that our design is something innovative? So here you can see the initial concept of our air brake. As you can see, we have 2 plates. It's pretty small. I don't know if y'all can see, but we have 2 plates, the upper and lower plate. These 2 plates are aligned to the rocket body diameter, so we won't have any problems or issues with holes or bumps that may affect either the drag, the stability, or the aerodynamic of the rocket. So we're using a mechanism also inspired and also known as the hover-mine style linkages. It's basically to have a synchronous motion, and it's something pretty straightforward, something simple. And as you can see, the upper plate has a longer link. This means that it will help to have a longer or farther deployment. And both plates are aligned. So, they're not the same size, but this will help us to have a better surface area. So for the fabrication of our air brake, as you can see, I'm holding it in my hands. We used some additive manufacturing techniques, basically to have higher strength. So we use carbon polylactic acid, or also known as carbon PLA. This helps us to print all of the parts, so all of the parts also are very strong. So we don't have issues with this. Here, this video shows one of the tests we did basically to see that the air brake was working correctly. We're using an Arduino, on a servo motor, and some sensors that will help us to control and read the data of altitude, of temperature and pressure. So that's how the mechanism works. So what I mean by this, so basically with the altitude, we're going to be able to deploy the air brakes or the plates. So yeah, I mean, we did some tests like this in the lab. We also did some load analysis. A load analysis basically put in the expected drag force in our plates. So just basically to see if the plates will hold the expected drag force. So, I mean, yeah, we did some simple analysis. Why? Because this is still a prototype. Our main goal is to basically see that the linkages, that the mechanisms, that everything will work as we expected. Oh, wait, what happened? Can you help me, please? It's number 6. Okay, sorry about that. Okay, so we did some computational fluid dynamics on this air brake. As you can see, this image, the one on the left side, basically shows the box where the air brake is positioned. So we did 2 comparisons. First, we're comparing the single plate, and we're comparing it to the MLPD, which is 2 plates. So as you can see, the left image shows the MLPD, the right image shows the single plate. There's a big difference with the velocity in our simulations. The MLPD has a velocity of 381 meters per second, I'm sorry. And the single plate has a velocity of 441 meters per second. This means that the MLPD is slower. There's a difference around 60 meters per second. So what are we trying to accomplish with the air brake to make the rocket slower? So, I mean, we're basically proving that the system is working correctly. As you can see, there's a big difference between the surface area. Our surface area has a difference of about 75%, meaning that the MLPD is really increasing by a lot our surface area. This means that also we have an increasement in drag coefficient and in the drag force. All of these values are for the whole system, just so you don't get confused. So there's a difference of 133 newtons for the whole system. And we actually did some tests with data we recorded from a previous launch with a 10K rocket. So we used the maximum speed, which was 267 meters per second. So we are using real data. We're not inventing something just to get a result or data. So we're using actual flight data. And after this, after having our simulations, after knowing that everything was going to work, we did some launch tests. The first one didn't went as expected. I don't know where I can play the, okay, so this video shows, it's a short video of how it went. This is the launch. Basically, it was to prove that the mechanism was working correctly, that the code, that the Arduino, that the sensor, everything was going to be functional. But we had a problem. We had a malfunction with the Arduino code, but we were able to recover the rocket. So everything, all pieces were together, so we were able, to later on to do another test launch. This was successful. We were able to recover the rocket, and I'm saying this was successful because here you can see the data. This is a text file from the data we obtained. There you can see the word deploy. That means that the air brake was deployed at the expected altitude. So since this was a level 2 rocket, so we thought of opening or deploying the air brake like around 1,500 feet. There's still a gap. As you can see, it was deployed 1,577 feet. There's still a gap, but we might think this be an error of the servo motor because it's not fast enough, or a problem with the sensor. So since this is a prototype, these are things that we still can change, can improve. And lastly, just to summarize, you saw that there's an improvement, an increasement in the surface area of the whole mechanism. So as I show you with the results, there's an increasement of 75% of the whole surface area of the mechanism. So as expected, we were able to increase the drag coefficient, the drag force. So there's this gap that, I mean, we can still improve by doing some changes. I mean, this is a 4-inch diameter, and since we're planning on actually using this airbag in future IREC competitions, our rocket has a diameter of 6-inch, so I mean, we need to scale it, we need to make it bigger, and we might have better results for the drag force. And yeah, I mean, as I said, right now we're getting the data from altitude. We're still thinking of changing the sensors, either to still controlling altitude, to change it to velocity. But I mean, this is still a work in progress since this is a prototype. And thank you all for being here. I know you will be hearing more of us. The rocket team is still growing. So if anyone has any questions, I'm more than happy to answer to you.
Yep. So on your test flight where it deployed, what was your expected apogee if you didn't have air brakes?
Mm-hmm.
What was that compared to your actual apogee?
So without air brakes, that was 2,500. So basically, I mean, we used Open Rocket to get this data, and then, yeah, as I said, it was 2,500. But now with the air brake, when deployed, it was going to be 2,200. So we got this data using MATLAB because we have a code with MATLAB basically to understand and to know when or at which altitude to deploy the air brake. So as I said, this was deployed at, well, the expected deployment was 1,500. So, I mean, yeah, so it changed from 2,500 to 2,200.
Okay. And then are you going to do a test flight with a 6-inch rocket before you go to IREC?
Yes, I mean, we actually need to do some tests. And as I said, this is a prototype. We still need to do some changes to actually like use it in our IREC rocket. So, I mean, yeah, we like during the year, we do some tests basically to make sure that everything is right. So we can compare the previous drag force without the air brakes and then compare it with the MLPD inside of the rocket. Does this answer the question?
Yeah.
Okay, okay. Any more questions? Okay, guess that's it.
Yeah.